In this video, we will discuss nuclear binding energy. What is nuclear binding energy? Well, to introduce this concept, we need to talk about mass defect. For example, let's take fluorine-19. Fluorine-19 has 9 protons, 10 neutrons, and 9 electrons. We know what the mass of these subatomic particles already is. And if we add up the masses of 9 protons, 10 neutrons, and 9 electrons, we get about 19.157075 atomic mass units. Now you may think this is very highly precise, and there's a reason why we're doing this at such high precision. Now if we measure the actual mass of the fluorine-19 atom, we get a slightly different number. The difference is what's known as the mass defect. So where did that mass go? Now you may notice that that value was negative. The mass defect in this case is negative because the mass that we ended with, if we were trying to construct this fluorine-19 atom, was less than the mass we started with the individual subatomic particles. That difference leads to the nuclear binding energy. Now, what is this nuclear binding energy, and what's the deal with it? Well, for this we have to go back to our old friend Einstein and his special relativity equation, E equals mc squared. Or in this case, the change in energy equals the change in mass times the speed of light squared. Now, these mass defects are very small, so we have to do these calculations at very high precision. So if we take our mass defect, which, as you recall, is negative, and we convert this to kilograms, we have a fairly small number. So if we wanted to create 1 atom of fluorine-19, the difference in mass is very, very small. Now we plug this into our E equals mc squared, and we get this number. But let's take a look at those units. Kilograms times meters squared per second squared. Well, this is the same as joules. It's a 1-to-1 ratio of joules to kilograms meters squared per second squared. This basically tells us the amount of energy that we would get out after constructing 1 fluorine-19 atom. Now, if we want to know how much energy we get out from a whole mole of fluorine-19 atoms, we just multiply this times Avogadro's number. And now we start getting into some serious energy. This is about 14 terajoules per mole. And again, this is negative, so this is exothermic. So we're talking about some pretty serious energy here. Now, the concept of the nuclear binding energy is very important, especially when it comes to something such as stellar nucleosynthesis. Stellar nucleosynthesis is where stars get their energy. In the very beginning, there was essentially just energy, and that's a lot of conjecture. Chemists don't really care until you get to the point where, at the beginning of the universe, there was hydrogen. Once this hydrogen comes together and starts to form enough gravity to start compressing itself, then we start fusing these hydrogen nuclei together to make deuterium. This involves a fair amount of energy. Then hydrogen combines with deuterium to make helium, gives you even more energy. And then finally, the helium-3 isotopes combine to give you your standard helium-4, plus 2 more hydrogen nuclei, which gives you even more energy. Now this is important because, again, this is where stars get their energy, and this is where we get heavier elements. Now you can take an astrophysics course or an astronomy course, and they can talk all about how we get different elements from inside various stars, depending on their size. But one thing that should be noted is that once you hit iron, the amount of energy you get out goes way down. In fact, the synthesis of heavier elements essentially ends with the formation of iron-56 inside stars. And that's because the combination of nuclei now requires energy rather than giving it off. And again, depending on the size of your star, that's going to give you different elements. Now, how do we get elements greater than iron and nickel? Well, once a star loses the energy production at its core, and that exact stage depends on its size, it begins to collapse in on itself. Now, large enough stars will go nova, and this is the entire mass of the star collapsing in on itself, combining those different nuclei into elements heavier than iron and nickel. Anything heavier than plutonium, Z94, has never been actually observed in nature. Elements 95 through 118 have only been synthesized, even if only a single atom has ever been observed in the lab. Now, if you're interested in stellar nucleosynthesis and the lifetime of stars, see the link in the comments of this video. So the process that we've been talking about that goes on inside stars is what's known as fusion, when you take nuclei and combine them in order to get heavier elements. The opposite of fusion is fission, the breaking apart of nuclei. And this is where we get our energy when we go approximately beyond Z number 70. In order to achieve fusion, you need tremendous amounts of heat and gravity in order to instigate these reactions. Fission is a little different. Now, one of the applications of nuclear fission is, in this example, the little boy atomic device. Now, uranium-235 was used in the little boy atomic bomb design. Uranium-235 is special because it can be easily split by the bombardment of neutrons. This process is called fission. Now, the metastable uranium-236 intermediate immediately splits into two daughter isotopes, producing energy and 3 more neutrons, which can go on to strike other atoms of uranium-235 in what's known as a chain reaction. Now, we can actually calculate the energy involved in this fission reaction. Now, if enough uranium-235 is collected, the neutrons produced through spontaneous fission will induce a chain reaction. This minimum mass is known as the critical mass. We can calculate the amount of energy produced by the complete fission of the critical mass of uranium-235 through a chain reaction using our mass defect calculation. Here we have the total sum mass of the reactants and the total sum mass of the products. We're going to calculate the difference and convert that into kilograms per mole. We find our mass defect. Now we plug this into E equals mc squared, and we get our energy produced per mole of uranium-235. Now, at a critical mass of 56 kilograms, we actually produce about 4 times 10 to the 12 kilojoules, or nearly a megaton of energy. Now, it should be noted that the original little boy device, which contained 64 kilograms of uranium-235, actually produced only 15 kilotons of energy. This low yield is due to the inefficient and incomplete fission of the uranium.